We just found the confidence interval for the expected value of y star. Now we actually want to find a prediction interval for y star itself. So this is not going to be a confidence interval because y star itself is not a parameter. The expected value of y star is a parameter, but y star itself is not a parameter. So what we're going to do is consider the error in estimating y star by y star hat. Okay, so y star minus y star hat will give us the error. And we're going to look at the expected value of that error. That's going to be the expected value of y star minus y star hat. So that's going to be the expected value of y star, which we know is beta 0 plus beta 1 x star plus epsilon. And then we're going to subtract the expected value of y star hat. That's going to be beta 0 hat plus beta 1 hat x star. Now the expected value of the first term, those first things are constant, beta 0 plus beta 1 x star. And the expected value of epsilon is 0. Then we're going to subtract the expected value of beta 0 hat, which is beta 0. And the expected value of beta 1 hat x star, that will be beta 1 x star. And notice that the expected value of the error is therefore 0 when I do the subtraction. Now what about the variance of the error? The variance is going to be the variance of y star minus y star hat. That, using our general formula for variance, is going to be the variance of y star plus the variance of y star hat minus 2 times the covariance of y star and y star hat. Now that minus sign comes from this minus sign right here. Okay, so let's look at that covariance term. The covariance of y star and y star hat, that's going to be the covariance of beta 0 plus beta 1 x star plus epsilon with beta 0 hat plus beta 1 hat x star. And that we can simplify by first noticing that beta 0 plus beta 1 x star, that's a constant. So that part in the covariance is going to go to 0. So what we're left with really is the covariance of epsilon with beta 0 hat plus x star times the covariance of epsilon with beta 1 hat. Now epsilon is just the random error, so it's going to be independent from both beta 0 and beta 1. So those covariances are going to be 0. So the covariance of y star with y star hat is going to be 0. So that means the variance of the error is really just going to be the variance of y star plus the variance of y star hat. Well, the variance of y star, that's going to come from epsilon, and that's going to be sigma squared. So the variance of epsilon is sigma squared. And then the variance of y star hat, that's going to be what we calculated before, 1 over n plus x star minus x bar squared over s sub xx times sigma squared. So what I'm going to do is factor out the sigma squared so that I get 1 plus 1 over n plus x star minus x bar squared over S of x sigma squared. Now, we can conclude that then y star minus y hat star, okay, both of those have a normal distribution, so that's going to have a normal distribution. We can see that the mean is 0 and that the variance is again going to be this big term with sigma squared in it. Now, another way that we could write that is we could take y star, subtract y star hat, and we can divide by standard deviation. So that's going to be sigma square root of 1 plus 1 over n plus x minus x star squared over S of xx. And now that we've divided by standard deviation, that's going to have a normal distribution, mean 0, standard deviation 1, or variance 1. But we don't know what sigma is, so we're going to estimate sigma by S. So that means if we replace the sigma here with S, then this is really not going to have a normal distribution, it's going to have a t distribution. The degrees of freedom in that case are going to be n minus 2. So knowing that, we can unwrap this large term here like we've done in the past to get us our prediction interval. So our prediction interval is going to be beta 0 plus beta 1 x star. These have hats on them. Plus t sub alpha over 2 s times the square root of 1 plus 1 over n plus x star minus x bar squared over S of xx. Okay, so our confidence intervals are always of this form, right, where we take the mean. In this case, the mean is, or the sample mean. In this case, that's the regression line, beta 0 hat plus beta 1 x star, right? Then we add the t-statistic times our standard error. In this case, our standard error is given by the s times that square root term. Our degrees of freedom here will be, again, n minus 2. And I want you to notice that if you compare this to the confidence interval that we found for expected value of y star, that the only difference is this 1 here in the square root. So we've added a 1 in the square root. And because of that, our prediction interval is going to be wider than our confidence interval for the mean. So the idea here is that our confidence interval for the mean is going to be narrower because the prediction interval is going to give us a sense of where 95% of the data may lie, whereas the confidence interval for the mean is a 95% confidence interval, for example, for the mean. Okay, let's use an example to illustrate all of this. Okay. So we're going to go back to this global temperature versus CO2 data. And we already found the regression line. And we already looked at some of these summary statistics. And so what I want to do is find a 95% confidence interval and a 95% prediction interval. And I'm specifically going to look at what happens when x star is 400. Okay, so in order to find the confidence interval, first I'm going to need to know what the standard deviation is, or the variance. So remember that the variance, s squared, is going to be the sum of the squares of the error divided by n minus 2. So in this case, that's given as 0.5, and then n minus 2 is going to be 59. And so that's going to be 0.00847. So that the standard deviation, which is the square root of that, is going to be 0.092. Our degrees of freedom for this problem is going to be 59. That's not actually going to be on our t-chart, so I'm going to just have to say that's about 60, and that is kind of close enough. And so our t-statistic, if we want to do a 95% confidence interval, is t sub 0.025 with 60. And I'm going to go back. I'm going to look at my t-distribution chart. I'm going to be interested in this column right there, so the last column that we've been looking at. I'm going to move down the chart to where it says 60. Notice that's in the column with the 95% confidence interval, and notice that it's 2.000. Okay, so in this case, my t-statistic is going to be, or my t for 0.025 in 60 degrees of freedom is going to be 2.00. Okay, from this, I want to construct the 95% confidence interval. So to do that, I'm going to put in the regression line 0.0105 x minus 3.3970 plus or minus the t value 2 times s 0.092 times the square root of 1 over n, which is 1 over 61, plus x star minus 353.76, that's x bar squared, divided by s sub xx, that's 46,332.88. And that's at x star. Now I'm going to plug in x star equals 400. Remember, that's parts per million for CO2 levels. And that's going to give us a confidence interval for the mean of 0.757 to 0.849. And those are in degrees Celsius. So the idea is when we have 400 parts per million of CO2 in the atmosphere, we're 95% confident that the mean CO2 level is going to be, that the mean temperature change is going to be between 0.757 degrees Celsius and 0.849 degrees Celsius. And that's our interpretation of the confidence interval for the mean. Now, what about our 95% prediction interval? So you notice that I'm copying this computation because I'm going to get a computation that is very, very similar for the prediction level. The only prediction interval, okay, the only difference is going to be in this formula for the standard error, and I need to add a 1 plus. Okay, so the prediction interval is almost identical, except for it's going to add the 1 plus. That's going to widen the interval. So for x star being 400 parts per million of CO2 in the atmosphere, okay, I'm going to get 0.613 to 0.993 degrees Celsius. Okay, so when we have 400 parts per million of CO2 in the atmosphere, we can predict that any data point that we get for the global temperature change will, with 95% probability, be between 0.613 degrees Celsius and 0.993 degrees Celsius. And that's the best interpretation for the 95% prediction interval. So let's look at these two graphs. you'll see that the 95% confidence interval for the mean, okay, notice that it's the narrower of the two interval. It does not contain many of the data points because it's supposed to be predicting the mean or the regression line, okay? Specifically at 400, we got that it was going to be between 0.757, which is about there, and 0.849. So you can see our x star equals 400 on that interval. Notice that the interval is narrower in the middle than it is on the ends, which is something that we saw before. Okay, and that gives us the 95% confidence interval for expected value of y star. Okay, but now look at the prediction interval. The prediction interval, you'll see that it contains most of the data points. In fact, it should contain about 95% of the data points. Okay, specifically at x star equals 400, right? We have a confidence interval of 0.613 to 0.993. Okay, so we have a much wider interval there. Okay, and you'll notice that the prediction interval in general is wider than the confidence interval. Okay, and one thing that you won't notice from this graph, but it is actually wider on the ends than it is in the middle. So we should observe that both intervals are wider at the ends than at the middle, and then the interval for predicting y star is wider than the confidence interval for expected value of y star.